Tonight, we're going to talk about something that most people never think about, not because the subject is obscure or technical or buried in scientific journals that nobody reads, but because the answer is hiding in plain sight, right above your head. Every time you step outside on a clear night and look up, the space between the stars, that black void you see when you look at the night sky, the darkness between the bright points of light, most people look at it and see nothing. They see emptiness, they see absence, they see the peaceful backdrop of the cosmos, a canvas on which the stars are painted, and for most of human history, that's what astronomers assumed it was, too. Nothing. A near-perfect vacuum, a vast, serene, eternal emptiness. By the end of tonight, you're going to understand why that assumption is wrong. Completely, profoundly, disturbingly wrong. The space between the stars isn't empty. It isn't peaceful. It isn't serene. It is one of the most violent, turbulent, actively hostile environments in the known universe. And the most disturbing part isn't even what's out there. The most disturbing part is what it means for us, right here, right now, on this planet, in this solar system, in this moment. Because here's something nobody tells you when you look up at the night sky. The space between those stars isn't something separate from us. It isn't somewhere else. We are in it. We live inside the interstellar medium. Earth moves through it right now. The solar system is plowing through this material at about 500,000 miles per hour. We have been traveling through this environment for the entire history of our planet, and the specific region of interstellar space we happen to be passing through right now. The stuff immediately surrounding our solar system was created by catastrophic stellar explosions. We are living inside the remnants of an ancient cosmic disaster. That's where we'll end up. But let's start at the beginning, because understanding what disturbs you about interstellar space requires understanding what people assumed it was, and then discovering, piece by piece, over decades of observation, exactly how wrong those assumptions turned out to be. Before we get started, if you love exploring the depths of space as much as we do, take a second to like the video or subscribe. It's a simple action, but it helps this channel reach more curious minds like yours. Now, let's begin. Let's start with the simplest question. What is the space between stars? Not theoretically, not philosophically. What is actually physically present in the gaps between the stars you see when you look up at night? The first thing you need to understand is that the word empty, when applied to space, is a relative term. A very relative term. In everyday life, empty means nothing. An empty room, an empty bottle, an empty parking lot. Nothing there. But in physics and astronomy, empty is a spectrum, not a binary condition. And the closest things we have to true emptiness in the universe are in our own physics laboratories on Earth, not in the depths of space. The space between stars, technically called the interstellar medium, or just the ISM if you're talking to astronomers, contains matter. Not much of it by any human standard, but not nothing. On average, a cubic centimeter of interstellar space contains about one atom, one single atom, in a volume the size of a sugar cube. Compare that to the air in the room where you're sitting right now. The air around you contains something like 25 million trillion atoms in that same cubic centimeter volume. The interstellar medium is roughly 10 million trillion times less dense than the air you're breathing. By any earthly measure, that is essentially nothing. If you built the best vacuum chamber ever constructed in any laboratory on Earth, pumped it down to the lowest pressure ever achieved, you would still have billions of atoms per cubic centimeter inside your chamber. The interstellar medium is more empty than any vacuum we have ever created. The most pristine, most meticulously evacuated laboratory environment in human history would look like thick soup compared to interstellar space. So yes, in that sense, the space between stars is almost incomprehensibly empty. Almost. But here is where things begin to get interesting. And by interesting, I mean deeply, fundamentally disturbing. Because even though interstellar space has almost nothing in it per cubic centimeter, the galaxy is enormous. The Milky Way is roughly 100,000 light-years across, and a light-year is about 6 trillion miles. When you multiply the almost nothing that's present in each tiny volume of space by the incomprehensible volume of the galaxy, you end up with something. A lot of something. Actually, the total mass of all the gas and dust in the interstellar medium of the Milky Way is estimated at several billion times the mass of the Sun. It's just spread so incredibly thin that any tiny region you look at seems empty. But the disturbing thing about the interstellar medium isn't just that it exists when you thought it didn't. The disturbing thing is what it actually is, what it's made of, what it's doing, what it has been doing to us From the moment this solar system formed, through the entire 4.5 billion years of Earth's history, up to and including right now as you read these words. Let's start with what the interstellar medium is actually composed of, because the composition alone should give you pause. About 99% of the interstellar medium is gas, and about 1% is dust, by mass. The gas is mostly hydrogen, the simplest and most abundant element in the universe, with helium making up most of the rest. There are also traces of heavier elements: carbon, oxygen, nitrogen, iron, silicon, all forged in the cores of stars that lived and died before our sun was even born. The dust is more interesting. Interstellar dust isn't like household dust. It isn't dead skin cells and textile fibers. It's mostly tiny solid grains, often a fraction of a micron in size, made of silicates and carbon-based compounds. These grains are literally the ashes of dead stars. When a star ends its life, either by shedding its outer layers as a planetary nebula or by exploding as a supernova, it scatters material into space. That material gradually cools, and some of it condenses into these microscopic solid particles. The dust drifting between the stars, right now, floating through the void, is the physical remnant of stars that died hundreds of millions or billions of years ago. When you look at a dark nebula, one of those black patches in the Milky Way that seems to block out the stars behind it, you're looking at an enormous cloud of this ancient stellar ash, so thick it blocks the light of stars beyond it. But even this, the gas and the dust, isn't the most disturbing part. There are three other components of the interstellar medium that most people never hear about, and together they transform our picture of the space between stars from something peaceful and empty into something that resembles a complex, active, violent environment that has been quietly shaping the destiny of every star, every planet, and every living thing in the galaxy. Those three components are magnetic fields, electromagnetic radiation, and cosmic rays. Let's take them one at a time, because each one deserves to be understood properly. The interstellar medium is threaded throughout with magnetic fields, not the kind of magnetic field you'd detect with a compass, much weaker than that, but magnetic fields nonetheless. Pervasive, galaxy-wide magnetic fields that permeate every cubic centimeter of interstellar space. The average magnetic field strength in the interstellar medium is only a few microgauss, which is genuinely tiny. Earth's magnetic field is millions of times stronger. You would never feel these interstellar magnetic fields with any human sense or any ordinary instrument. But what these fields do matters enormously. They control the motion of charged particles in interstellar space. Charged particles, things like protons and electrons and atomic nuclei, cannot simply move in straight lines through a magnetic field. The field forces them to spiral around the field lines, tracing out helical paths. This matters because much of what's in the interstellar medium, once it becomes ionized, once the atoms lose their electrons and become charged plasma, is forced to follow the magnetic field geometry rather than flowing freely. The magnetic fields act like invisible highways, channeling material, directing flows, structuring the otherwise random cloud of gas into organized patterns. And here is something that research published in 2025 has started to clarify in detail. These magnetic fields are not static. They are constantly being disturbed, twisted, amplified, and restructured by turbulence, by the energy injected into the interstellar medium by dying stars, by stellar winds, by supernova explosions. The magnetic structure of the interstellar medium is a dynamic, constantly changing architecture, and it plays a role in regulating everything from how quickly new stars form to how energy is transported across the galaxy. A 2025 simulation study found that turbulence in the interstellar medium is crucial for redistributing energy and creating the complex multi-phase structure we observe. The interstellar medium isn't a simple passive medium, it's an energetically active system. Then there's the electromagnetic radiation. The interstellar medium isn't dark, even far from any star. Even in the deepest spaces between stellar systems, space is bathed in radiation. Visible light from every star in the galaxy is streaming through interstellar space, diluted across distances, but present. Ultraviolet radiation from hot young stars ionizes the hydrogen gas near those stars, creating glowing regions called HII regions. Infrared radiation from warm dust grains illuminates cold dark clouds. X-rays from hot gas and from violent events fill the galaxy with high-energy photons. The cosmic microwave background, that ancient relic radiation from the Big Bang itself, permeates every cubic centimeter of space, with photons carrying the afterglow of creation. Even in the absolute darkness between stars, there is light. Not enough to see by, not enough to feel, but light nonetheless, filling space with energy, driving chemistry in cold molecular clouds, ionizing atoms, heating gas, influencing the conditions in which new stars and planets will eventually form. But none of this, not the gas, not the dust, not the magnetic fields, not the radiation, is what I want to spend the most time on, because all of that is relatively peaceful compared to the third hidden component of the interstellar medium. Cosmic rays. Cosmic rays are, to put it plainly, one of the most terrifying things about the universe, and you've almost certainly never thought about them much, because they don't make the headlines and they don't have the dramatic visual appeal of black holes or supernova or galaxy clusters. But they are happening right now. They are happening to you, right now, as you read this. And understanding what they are and where they come from fundamentally changes how you see the space between the stars. A cosmic ray is a high-energy particle, usually a proton or an atomic nucleus, traveling through space at very nearly the speed of light. We're talking about energies that are genuinely staggering. Some cosmic rays have been detected with energies equivalent to a baseball thrown by a pitcher, concentrated into a single subatomic particle. Imagine a proton, an object 100,000 times smaller than an atom, moving at 99.99% of the speed of light. The energy packed into that single particle is macroscopic. You could feel it if you held out your hand and let it hit you. Just one particle, the most energetic cosmic rays ever detected, have energies exceeding the energy of a bullet fired from a rifle, concentrated into an object smaller than any microscope can resolve. These are called ultra-high-energy cosmic rays, and they are so energetic that their origin is still debated. Something out there in the universe is accelerating particles to speeds so close to the speed of light that the distinction between the particle's speed and the speed of light itself is measured in parts per billion. Where do cosmic rays come from? Mostly from supernova. When a star explodes in a supernova, it releases an amount of energy equivalent to the total light output of our Sun over its entire 10 billion year lifetime, all at once, in seconds. Some of that energy goes into creating a shockwave, an expanding bubble of material moving outward at thousands of miles per second. That shockwave is a particle accelerator. Protons and atomic nuclei that get trapped in the turbulent magnetic fields near the shockwave bounce back and forth across it, gaining energy with each crossing, like a ball bouncing between two moving walls that are coming together. Each bounce accelerates the particle more. If a particle crosses the shockwave enough times before escaping, it can end up traveling at speeds indistinguishable from the speed of light, carrying extraordinary amounts of energy. And then these particles stream through the galaxy. They don't travel in straight lines, because the galaxy's magnetic fields constantly deflect their paths. They spiral, they scatter, they ricochet off magnetic irregularities. A cosmic ray particle might spend millions of years wandering through the galaxy before it finally hits something or escapes into intergalactic space. The galaxy is permeated with them at all times, from all directions, created by supernova that exploded decades and centuries and millennia ago. Right now, several cosmic ray particles are passing through your body every second. Most of them are the lower energy ones, the ones that sneak in through the atmosphere's gaps, or penetrate just enough to leave a tiny ionization track through a few cells. You will never feel them. You will never know they are there, but they are there. They have been passing through you every second of your life. The atoms in your body are constantly being struck by particles that originated in stellar explosions light years away. Particles that have been traveling through the galaxy since before your parents were born, since before recorded history, perhaps since before our species existed. Earth's magnetic field, generated by the churning molten iron in our planet's core, deflects many of the lower energy cosmic rays before they reach the surface. Earth's atmosphere absorbs or transforms others. When a high-energy cosmic ray hits the upper atmosphere, it triggers a cascade of secondary particles that spray downward like a brief cosmic shower. Billions of particles created in a fraction of a second from the energy of that single incoming proton. These secondary particles are what actually reach the ground. Your body is a detector for the aftershocks of ancient stellar explosions. Now, here is where the story gets genuinely disturbing. Earth's magnetic field and atmosphere protect us from most cosmic ray damage. This is important. This protection is real and it matters. Without it, we would not be here. The biosphere as we know it depends on this shielding, but that shielding is not absolute. It is not permanent, and there are conditions under which it fails. Specifically, there are conditions under which the cosmic ray flux hitting our planet increases dramatically, overwhelming our defenses. Those conditions include nearby supernova. Astronomers have carefully calculated the danger zone for supernova and life on Earth. A supernova exploding within about 25 to 30 light-years of our planet would be catastrophic. The initial burst of gamma rays and X-rays would arrive in essentially no time. Given that both travel at the speed of light, these would begin stripping away our ozone layer, the thin shield in the stratosphere that protects surface life from the sun's ultraviolet radiation. Then, over the following months and years, X-rays produced by the supernova's interaction with surrounding gas would arrive. And then, over decades and centuries following the explosion, the cosmic rays, the particle shockwave, would reach us, providing a sustained bombardment that would continue to batter the atmosphere and increase mutation rates globally. The ozone damage alone could trigger mass extinctions. Ultraviolet radiation from the sun would reach the surface at intensities that could severely harm photosynthesis, burn the skin of animals, damage marine life that lives near the ocean's surface. Food chains would collapse. Ecosystems would be restructured by whoever was tough enough to survive. 25 to 30 light-years is not a large distance by astronomical standards. The nearest star to our sun is just over 4 light-years away. The stellar neighborhood we live in contains hundreds of stars within 100 light-years. Over the lifetime of our solar system, supernova within the danger zone have certainly occurred. And here is where it gets personal. Here is where the story of the interstellar medium stops being abstract and starts being about us, specifically, about this planet, about our own existence. The solar system is not where it has always been in the galaxy. Every 225 million years or so, the sun completes one full orbit around the galactic center, and the neighborhood it passes through changes over that time. Different spiral arms, different stellar densities, different environments, but more relevantly, over shorter timescales of tens of millions of years, the sun's trajectory takes it through different local environments, different clouds of gas, different regions of higher or lower stellar density. About 5 to 10 million years ago, by current estimates, the solar system wandered into a specific region of space, and that region had recently been devastated. Let me tell you about the local bubble. If you could somehow zoom out and look at the structure of the galaxy on scales of hundreds of light-years, you would see a pattern. The interstellar medium is not smoothly distributed. It is clumpy. It has clouds and voids and shells and filaments. Stars are not scattered uniformly through space. They cluster in stellar associations, groups of stars that formed from the same molecular cloud and are still moving together through the galaxy. In our neighborhood of the Milky Way, we would see something striking. Surrounding our solar system, in all directions, there is a cavity, a region where the gas has been swept away, where the density of interstellar material is drastically lower than average. Instead of the typical density of the interstellar medium, roughly half an atom per cubic centimeter, the space immediately surrounding our solar system has a density of only about 1/20th of that. It's nearly empty compared to what lies beyond it. This cavity is roughly 1,000 light-years across. From our position near its center, in all directions, there is this low-density region before you reach the denser walls at its edges. And those walls, the edges of this cavity where the gas piles up in a thin compressed shell, are precisely where a remarkable amount of star formation is currently happening. Young stellar clusters ring the edge of this cavity as if they were assembled there, triggered into birth by some event. This cavity is called the local bubble, and we live inside it. The local bubble is not a quiet, peaceful, empty space. It is a crime scene. It is the aftermath of a series of stellar explosions. Astronomers believe the local bubble was created over the last 10 to 20 million years by something between 15 and 20 supernova, massive stars in what was then a nearby stellar association. A cluster of hot massive blue stars that formed together and then, one by one, exhausted their fuel and exploded. Each explosion sent a shockwave outward, expanding into the surrounding interstellar gas, sweeping it up, compressing it, heating it. The successive explosions reinforced each other, creating a collective cavity as they cleared out the gas in a large volume around themselves. What we call the local bubble is the accumulated remnant of those explosions. The walls are where the swept-up gas piled up. The stellar nurseries at the walls are where that gas was eventually compressed enough to collapse into new stars. The interior of the local bubble, the space we actually live in, is filled with a remarkable substance. It is not empty vacuum, it is plasma. ionized hydrogen and helium gas, stripped of their electrons by the heat of the supernova explosions that created the bubble. And this plasma is hot, incomprehensibly hot by any human standard. The local hot bubble, as it is sometimes called to distinguish the hot interior from the cold shell at its edges, contains gas at temperatures of roughly 1 million Kelvin, 1 million degrees. The surface of the Sun is about 5,800 Kelvin. The interior of the local bubble, the gas surrounding our solar system on all sides, for hundreds of light years in every direction, is roughly 200 times hotter than the surface of the Sun. Let that sink in. We live inside a bubble of plasma that is 200 times hotter than the Sun's surface, and yet you've never noticed, you've never felt it. And there's a reason for that, which we'll get to in a moment, but first appreciate the raw fact. Right now, surrounding our solar system, for hundreds of light years in all directions, there is a plasma heated to 1 million degrees. The gas between us and the nearest stars is not cold, empty darkness. It is a thin, incredibly hot, incredibly sparse plasma, glowing faintly in X-rays, a remnant of stellar catastrophes that played out millions of years before the first humans existed. The reason you can't feel it is the reason we discussed earlier. Temperature is a property of matter, a measure of how fast particles are moving. The local hot bubble has gas moving at extraordinary speeds, which means high temperature, but the density is so incredibly low, only about 5/1000ths of an atom per cubic centimeter, that there is almost nothing to transfer that energy to anything else. You would have to encounter almost no particles per second. The thermal energy is real, but there is so little matter that it would take extraordinarily long to transfer significant heat to any object. It's like being surrounded by thousands of bullets flying in all directions, but so spread out that you would go years without ever being hit by one. Still, the fact remains, the space between us and our nearest stellar neighbors is not the quiet, empty darkness of popular imagination. It is a million-degree plasma created by multiple stellar explosions. Our Sun and solar system are passengers moving through the aftermath of ancient violence. In October 2024, researchers using the EROSITA X-ray telescope published results showing not only the temperature structure of the local bubble in unprecedented detail, but also discovered a new interstellar tunnel connecting our bubble to a neighboring superbubble. These aren't isolated features. They're a connected network of supernova-carved cavities throughout our region of the galaxy, each one the product of stellar catastrophes, linked together by tunnels through which the hot gas can flow. The Milky Way, in the neighborhood where we live, is a Swiss cheese of supernova remnants. We exist in one of the holes. Now, a 2025 study published in the astrophysical journal Letters provided something even more striking. The local bubble didn't just reshape the gas around us, it may have reshaped life on Earth. About 6 million years ago, the solar system began entering the local bubble, according to current models. At roughly the same time, the fossil record and geological evidence show Earth experiencing significant environmental changes. The cooling of global temperatures, the expansion of grasslands and savannas, the reshaping of ecosystems. It was during this period that the lineage leading to modern humans began diverging from other primates. The environment was forcing adaptation and selection. Something was driving change. The 2025 study by Caitlin Nogiri and colleagues examined what the elevated cosmic ray flux from the nearby supernova that created the local bubble would have done to Earth. Their finding was remarkable. The cosmic rays from those supernova explosions would have penetrated Earth's atmosphere more easily during periods of reduced solar wind protection, increasing the background radiation at ground level, increasing mutation rates globally, and potentially driving evolutionary change through selection pressure on populations. The cosmic radiation may have been one of the environmental pressures that drove the diversification and adaptation of early hominids. The very supernova that created the bubble we live in may have left fingerprints on the evolution of our species. We have physical evidence for nearby supernova, not ancient theoretical reconstruction, but physical evidence embedded in the geology of our planet. Iron-60 is a radioactive isotope of iron. It is produced in supernova explosions and has a half-life of about 2.6 million years. You would not expect to find it in deposits here on Earth unless it came from somewhere that had recently experienced a supernova, but we have found it. Iron-60 has been discovered in layers of seafloor sediment, in Antarctic ice, and in lunar samples, concentrated in deposits that date back to roughly 2.5 to 3 million years ago, the start of the Ice Ages and the Pleistocene epoch. Something exploded near us around that time. close enough that the radioactive debris from the explosion was captured by Earth's gravity and settled into the sediments at the bottom of our oceans. That iron 60 is sitting in the ocean floor right now, the physical residue of a supernova. Atoms created in the death of a star, scattered across interstellar space, falling onto our planet. The ocean is a library, and its sediments record not just the history of life on Earth, but the history of the cosmos around us. The timescales and distances involved suggest we are talking about at least one supernova within perhaps a few hundred light years, close enough to rain iron 60 onto our planet in quantities we can still detect today. The research connecting the local bubble's supernova history to the radiation record in Earth's crust is ongoing, and the full picture is still being assembled, but the evidence is clear that our cosmic neighborhood is not and has never been truly quiet. Now, let's talk about something even more immediate than ancient supernova remnants. Let's talk about the ongoing violence of the interstellar medium that is happening right now, constantly, everywhere between the stars. The interstellar medium is not an equilibrium. It is not a quiet, stable environment, gently drifting through space. It is turbulent, deeply, chaotically, perpetually turbulent. The turbulence in the ISM is driven by a hierarchy of processes, from the largest scales to the smallest. At the largest scales, entire spiral arms create density waves that propagate through the galaxy, compressing gas and triggering star formation on scales of thousands of light years. At intermediate scales, supernova explosions and the strong stellar winds from massive stars send shockwaves expanding outward at thousands of miles per second, slamming into the surrounding medium, compressing it, heating it, creating turbulent eddies that cascade down to smaller and smaller scales. At the smallest scales, the turbulence is maintained by the interactions between gas molecules, magnetic fields, and the ever-present cosmic ray particles that carry their energy through the medium. The result is that the interstellar medium is constantly in motion, constantly being mixed, constantly being shocked. Gas that was cold and quiet in a molecular cloud gets hit by the shockwave from a supernova and suddenly finds itself compressed, heated, and turbulent. Heated gas that was quietly drifting through the hot phase of the medium encounters a cool, dense cloud and begins to mix along the interface, creating unstable layers where hot and cold gas coexist and exchange energy in complex ways. Magnetic field lines are stretched and amplified by turbulent flows, creating regions of intense localized magnetic field that can channel gas, slow down or deflect cosmic rays, and accelerate particles to high energies. A 2025 simulation paper from a team of astrophysicists showed that this turbulence is not just noise in the system. It plays a fundamental role in creating the multi-phase structure of the ISM. The coexistence of gas at wildly different temperatures and densities in the same regions of space. Without turbulence, you would have simple, stable phases. With turbulence, you have a complex, constantly evolving medium that resists simple description. The turbulence mixes hot and cold gas, creating intermediate temperature regions that would otherwise be thermally unstable. It drives the formation of the dense cold clumps that eventually become molecular clouds and then stars. It regulates how much energy stars can dump back into their surroundings. It determines the efficiency of star formation across the galaxy. And all of this entire complex, turbulent, violent, magnetic, radioactive, multi-phase medium, this is what the space between stars actually is. This is what lies between here and the nearest star. This is what Voyager 1 is traveling through right now. Speaking of Voyager, let's pause and appreciate what this spacecraft has taught us about the actual boundary between our solar system and the interstellar medium, because the story is both more dramatic and more subtle than most people know. As of this spring of 2026, Voyager 1 is approximately 172 astronomical units from the Sun. That's about 16 billion miles. It's been traveling since 1977, nearly 50 years, and it is still operating. It crossed what astronomers call the heliopause, the boundary between the Sun's solar wind and the interstellar medium. In August of 2012, it became the first human-made object to enter interstellar space. And what did it find when it crossed that boundary? Surprise after surprise. The heliopause is not a simple sharp boundary. It's a complex transition region, and what lies on the other side, the actual interstellar medium, turned out to be denser than expected. The plasma density in the interstellar medium, just beyond the heliopause, as measured by Voyager's instruments when they detected oscillations in the plasma in 2013, was about 10 times higher than the solar wind density at the same distance. The interstellar medium is denser than the solar wind had been in the outer reaches of the heliosphere. The magnetic field direction, which was expected to change at the heliopause, turned out to be more aligned with the solar magnetic field than expected, suggesting that the heliosphere has been sculpting and organizing the local interstellar magnetic field. The two environments are not simply juxtaposed, they interact. The solar system pushes against the surrounding interstellar medium like a bubble moving through a fluid, and the fluid pushes back. Voyager also detected that the interstellar medium beyond the heliopause is hotter than expected, around 40 to 50,000 Kelvin, not the million-degree plasma of the wider local bubble, but hotter than astronomers had anticipated for the local interstellar cloud, the specific small cloud of interstellar material that our solar system is currently embedded in. This local cloud, sometimes called the local interstellar cloud, has a density of about 0.3 atoms per cubic centimeter, which is much higher than the interior of the local bubble, suggesting that the solar system is currently passing through or near a denser cloudlet within the overall hot bubble. Voyager 1, that tiny machine launched by humans 49 years ago, currently more than 16 billion miles from home, is still sending back data. As of late April 2026, 2 instruments remain in operation. It has become our probe into interstellar space, measuring conditions in an environment that no human will ever physically visit in our lifetimes. It is traveling through the very medium we have been discussing, the turbulent, magnetized, cosmic ray-filled plasma between the stars, and the conditions it finds, while expected in broad outline, continue to produce surprises in the details. The journey Voyager is on will take it through the local interstellar cloud for another 10,000 years or so, by astronomers' estimates, before it emerges into the wider, hotter, sparser gas of the local bubble's interior. Then it will travel for roughly 25,000 years before reaching the edge of the local bubble and entering the denser interstellar medium beyond, at which point, of course, Voyager will have been dead for millennia. Its nuclear power source will have run down within the next decade or so, but it will continue its journey, cold and dark, carrying its golden record, traveling through the same medium that has surrounded this solar system for its entire existence. Now here is something that should genuinely unsettle you. The local bubble's walls, those compressed shell regions at the edges of the bubble where the swept-up gas has accumulated, are not static, they are moving. The whole structure is still expanding, though slowly now. The initial explosive energy of the supernova long since dissipated into the kinetic energy of the slowly expanding shell. As the walls expand outward, they compress the gas ahead of them. New stars form in the compressed regions. Those new stars live their lives, and the massive ones among them eventually die in their own supernova explosions, potentially reinflating or reshaping the bubble. This is the cycle of the galaxy. Stars form, live, die, and in dying they shape the environment for the next generation of stars. The interstellar medium is the medium through which this cycle plays out. It is the reservoir that feeds star formation and the sink that receives the ejector of stellar death. It is both the graveyard and the nursery of stars. Our solar system formed about 4.5 billion years ago out of interstellar material, gas and dust that was enriched by previous generations of stars. The carbon in your cells, the oxygen you breathe, the iron in your blood, all of it was synthesized in the cores of stars that died before the sun was born and scattered their ashes into the interstellar medium. The solar nebula that collapsed to form our sun and planets was made of that recycled material. We are, in the most literal sense, made of the interstellar medium. We are assembled from the ash of dead stars, and the interstellar medium doesn't just connect us to our past, it connects us to everything around us in real time. Through the cosmic ray flux, through the passage of stellar shockwaves, through the slow drift of interstellar clouds, through the occasional close approach of other stars, the galaxy is not a collection of isolated star systems. It is an interconnected ecosystem, where events in one place ripple outward and affect conditions everywhere else over time. The close approaches of other stars deserve particular attention here, because they represent one of the most unsettling aspects of our long-term situation. The stars in our galaxy are not static. They are all in motion, orbiting the galactic center, each on its own trajectory, with slight variations in speed and direction that cause them to drift slowly relative to each other over millions of years. Most of the time, these relative motions are inconsequential. Stars are so far apart that their gravitational interactions are negligible, but occasionally, Rarely, a star passes close enough to our solar system to matter. And close, in this context, can mean something different from what you'd expect. The outer reaches of our solar system extend far beyond the planets. Neptune, the outermost planet, orbits at about 30 astronomical units from the Sun. But the solar system doesn't really end at Neptune. Beyond Neptune lies the Kuiper Belt, extending out to perhaps 50 astronomical units, full of icy bodies and dwarf planets like Pluto. And beyond the Kuiper Belt lies the Oort cloud, a vast spherical shell of icy bodies that extends all the way out to perhaps 1 to 2 light-years from the Sun. The Oort cloud is the reservoir of long-period comets. It is the outermost gravitationally bound region of our solar system, and it is incredibly fragile. The icy bodies in the Oort cloud are bound to the Sun by the weakest possible gravitational threads, orbiting so slowly and so far away that almost any external perturbation can knock them loose. When another star passes within a few light-years of our Sun, its gravity can disturb the Oort cloud. It can reach in gravitationally and perturb the orbits of thousands or millions of icy bodies at the edge of our solar system. Some of these bodies get deflected inward, toward the Sun, becoming long-period comets that eventually reach the inner solar system. Historically, periods of elevated comet flux have been proposed as drivers of mass extinction events on Earth. A large comet hitting Earth could be just as catastrophic as an asteroid, so passing stars, through the seemingly gentle agency of their gravity acting on the distant Oort cloud, can trigger comet showers that rain down on the inner solar system millennia later. The effects are delayed by the vast distances involved, but they are real. The timeline from stellar close approach to comet impact could be millions of years, but the causal chain is there, and these close approaches happen. Not on human timescales, not on historical timescales, not even on civilization timescales, but on geological timescales. They are regular events. Calculations suggest that a star passes within 1 to 2 light-years of our Sun roughly, every few 100,000 to million years, close enough to significantly disturb the Oort cloud. Over the 4.5 billion-year history of the solar system, this has happened thousands of times. Some fraction of the comets currently in the Oort cloud were perturbed there by stellar encounters long ago. Some of the periodic comets we observe, including some that have struck the inner planets in the distant past, may owe their existence to a stellar flyby that happened hundreds of millions of years ago. The star Gliese 445, a small red dwarf, currently about 17 light-years from us, is moving toward our solar system. Calculations show it will make its closest approach in about 40,000 years, passing within roughly 3.5 light-years of the Sun. That's close enough to be in the neighborhood, but not close enough to cause serious Oort cloud disruption. But other stars, not identified yet because we can't track all of them with sufficient precision, may have been closer in the past, or may approach more closely in the future. The galaxy keeps moving, the stars keep drifting, and every once in a great while, one passes close enough to knock on the outer door of our solar system. Now let's talk about something that happened last year that made this whole discussion viscerally real in a way that even dedicated astronomers found striking. Because in 2025, we had a visitor. On July 1st, 2025, a telescope belonging to the Atlas Survey Network, the Asteroid Terrestrial Impact Last Alert System, operating in Chile, picked up a faint moving object. Within days, as multiple observatories around the world tracked it and computed its trajectory, the stunning conclusion emerged. This object was not from our solar system. It was an interstellar comet, arriving from the direction of the constellation Sagittarius, traveling through our solar system on a hyperbolic trajectory that would take it in, around the Sun, and back out into the galaxy forever. This was the third confirmed interstellar object to pass through our solar system. The first was Oumuamua, the mysterious cigar-shaped object discovered in 2017 that generated enormous controversy and speculation. The second was 2I Borisov in 2019, a more clearly cometary object. The third was this new arrival, designated 3I ATLAS. 3.1 Atlas was remarkable on multiple levels. When it was discovered, it was traveling at roughly 137,000 miles per hour relative to our Sun. That speed is characteristic of an object from interstellar space, moving far faster than objects in our solar system. Pulled inward by the Sun's gravity, it accelerated to about 153,000 miles per hour at its closest approach to the Sun in late October 2025. NASA's Hubble Space Telescope imaged it on July 21, 2025. revealing a teardrop-shaped cloud of dust surrounding its solid, icy nucleus. Spectroscopic analysis identified the same kinds of molecules found in comets in our own solar system: water, carbon monoxide, and other volatiles. But the ratios were different. The composition was alien. This object formed in a protoplanetary disk orbiting a star somewhere else in the Milky Way, billions of years ago. How old was it? The estimates are striking. Astronomers calculated that 3I Atlas may be at least 7 billion years old, possibly as much as 10 billion years old. Our solar system is only 4.5 billion years old. This comet was formed before our Sun existed. It has been wandering through interstellar space, potentially for billions of years, since before Earth was born. It has traveled through the same interstellar medium we've been discussing, buffered by the same cosmic rays, exposed to the same starlight, drifting through the same sparse plasma for an almost incomprehensible span of time. And then, last year, it passed through our solar system. Briefly, a flash of cosmic history passing through our neighborhood. Hubble and other telescopes captured its images, analyzed its composition, measured its rotation. A spin period of about 16 hours, and then it moved on, swinging around the Sun and heading back out into interstellar space, never to return, carrying whatever secrets it holds about its origin and its billions of years of wandering. The discovery of 3 interstellar objects in about 8 years tells us something important. They are not rare. We have only the capability to detect the largest ones, the ones that get close enough to the Sun and are big enough to be visible at the distances we find them. But extrapolating from the detection rate, the implication is that interstellar objects are continuously passing through our solar system, not just occasionally, not once a generation, but constantly. The inner solar system, the region inside the orbit of Jupiter, is estimated to contain dozens of interstellar objects at any given time. They are streaming through, undetected, too small or too distant to see. Interstellar space is not the barrier we imagined it to be. Objects cross it. They cross it all the time. The galaxy is constantly shipping material between star systems, like a vast, slow postal service running on gravity instead of engines. Comets ejected from other solar systems travel through the interstellar medium for billions of years and arrive, briefly, in our neighborhood. Our own solar system has almost certainly ejected objects into interstellar space throughout its history, objects that are right now passing through the vicinity of other stars. When we look up at the night sky and feel the vastness and isolation of interstellar space, we are missing something important. Things are moving through that space, always. And this brings us to perhaps the most philosophically disturbing aspect of the whole picture. Not the violence of the interstellar medium, not the cosmic rays, not the ancient supernova remnants, not the passing stars, not even the interstellar visitors. The most disturbing thing is the implication about continuity, about connection, about what it means to be situated in the galaxy. There is no sharp line between our solar system and the rest of the galaxy. The heliosphere, the bubble of solar wind that encloses our planetary system, is a real and identifiable boundary. Voyager crossed it. The solar wind inside it is clearly different from the interstellar medium outside it. But it is not a wall. It is a permeable boundary. Cosmic rays pass through it freely, the higher energy ones penetrating all the way to Earth's surface. Interstellar objects pass through it on their way through the solar system. Starlight from the entire galaxy penetrates it. The heliosphere offers some protection from the low-energy particles of the interstellar medium, but it is not a fortress. It is more like a thin membrane. Outside that membrane, in all directions, is the interstellar medium. Right now, the heliosphere is being pressed against by a gentle but real wind of interstellar material. Particles and gas from the local cloud streaming past at about 50,000 miles per hour relative to our Sun. The heliosphere is slightly lopsided because of this. The leading edge, the side facing the direction of our motion through the interstellar cloud, is compressed. The trailing edge stretches out into a long tail. Our solar system is not a sphere in space. It is more like a comet, with a rounded head and a stretched tail, being pressed by the wind of interstellar material constantly flowing past. Embedded in that wind are the fingerprints of everything that has happened in this part of the galaxy for millions of years. The cosmic rays accelerated by the supernova that created the local bubble, the elevated flux of iron-60 from more recent stellar explosions, the interstellar dust grains that formed in the winds of dying stars and have been drifting through space for millions of years. All of this material is flowing past us, around us, through us, right now. This is the reality. This is what lies between the stars. Not peaceful emptiness, but an active, turbulent, violent medium connecting all stellar systems together. A medium that carries the history of every star that has ever exploded. Every supernova that has scattered its ashes into the galaxy. Every stellar wind that has blown gas into the void. A medium that is being driven, stirred, and shaped by ongoing processes that dwarf anything our civilization has ever experienced. Now, let me put all of this together, because it changes something fundamental about how we should think about our planet and our place in the cosmos. We like to think of Earth as isolated, separate, protected, sitting in its bubble of space, circling its star, going about its geological and biological business, largely independent of the wider universe. The space between us and other stars seems so vast, so empty, so absolute, that the idea of the broader galaxy touching us, affecting us, shaping our fate, seems like something you have to think very hard to make relevant. But the interstellar medium makes it immediate and direct. The galaxy reaches into our solar system through cosmic rays. Every second of every day, particles from stellar explosions light years away, penetrating everything we are and have ever been. The galaxy shaped the bubble we live in through the violence of ancient supernova that cleared out the gas around us and left us in a million-degree plasma. The galaxy delivers visitors, interstellar objects like 3I Atlas, crossing from other stellar systems and passing through ours, carrying chemistry from elsewhere in the Milky Way. The galaxy threatens our Oort cloud through the slow, patient gravitational perturbations of nearby passing stars, occasionally sending comet showers inward toward Earth. We are not separate from the galaxy. We are embedded in it. We are connected to it through the interstellar medium in ways that are ongoing, active, and significant. And here is the truly extraordinary part. The interstellar medium that connects us to the rest of the galaxy is the same medium that builds stars. Every star you see in the night sky assembled itself from this material. The Sun formed from a collapsing cloud of it 4.5 billion years ago. The planets formed from the dust and gas left behind in the solar nebula. You were assembled from atoms that, before the Sun existed, were drifting through the interstellar medium as part of a molecular cloud. Before that, those atoms were forged in the cores of stars that preceded the Sun. Before that, some of them were created in the first few minutes after the Big Bang, hydrogen and helium from the primordial fireball. The atoms in your body have been part of stars, part of interstellar clouds, part of the diffused hot plasma of supernova remnants, part of cold, dark molecular clouds where new stars are forming. They have been through every phase of the interstellar medium. They have been cosmic rays when they were accelerated in supernova shockwaves. They have been part of interstellar dust grains. They have been part of comets and asteroids. And now they are part of you, reading this. Tomorrow they will be elsewhere. Eventually, they will return to the interstellar medium, when the Sun eventually expands and Earth is destroyed, scattering the remains of our planet back into the galaxy. We are not just observers of the interstellar medium. We are temporary expressions of it. Organized complexity that the medium briefly adopts before returning to its diffuse equilibrium. Now let me spend some time on something that is not sufficiently appreciated. The interstellar medium is not the same everywhere. It is not a uniform substance spread evenly through space. It has phases, multiple distinct phases, that coexist in the same region, and the boundaries between them are where some of the most interesting and violent physics takes place. Astronomers describe the interstellar medium as multiphase. The three main phases are the hot ionized medium, the warm medium, and the cold medium. And they have dramatically different properties that you might not expect to find coexisting. The hot ionized medium is the stuff we've already talked about. Temperatures of 1,000,000 degrees or more. Extremely low density. Fills large volumes. This is the gas in supernova remnants, in the local bubble and similar structures scattered throughout the galaxy. This gas emits X-rays, which is how we detect and study it. It has been heated by supernova explosions and takes tens of millions of years to cool back down. Then there is the warm medium. This exists at temperatures of roughly 8,000 to 10,000 Kelvin and densities of about 1/10 of an atom per cubic centimeter. It is partially ionized, maintained in that state by ultraviolet radiation from nearby stars. This is the gas that fills much of the galaxy between the hotter and cooler phases. It's the background medium, the default state when you're not in a particularly hot region or a particularly cold one. Then there's the cold, neutral medium. Temperatures of roughly 50 to 100 Kelvin, -300 degrees Fahrenheit or so. Densities of tens to a few hundred atoms per cubic centimeter. much higher than the warmer phases. These are the cold clouds, regions where the gas has cooled enough that atoms are no longer ionized. Hydrogen exists here as neutral atoms. This is where molecular clouds form, where the temperatures drop even lower, 10 to 30 Kelvin, cold enough for molecules to form on grain surfaces, for complex organic chemistry to proceed, for gravitational collapse to begin and new stars to be born. Now here's what should genuinely shock you. These three phases coexist. In the same region of space, within volumes of perhaps a few hundred light years, you can have gas at 1,000,000 degrees, right next to gas at 100 Kelvin, a factor of 10,000 in temperature difference, right next to each other, not smoothly transitioning, right next to each other, separated by thin, turbulent, chaotic interfaces. How is this possible? Why doesn't the hot gas simply heat the cold gas and equalize? The answer is that in a very diffuse medium, the timescales for heating and cooling are extremely long. The hot gas expands away before it can transfer much energy to the cold clouds. The cold, dense clouds can radiate energy away as infrared radiation faster than they absorb it from the surrounding hot plasma. The magnetic fields help maintain the pressure balance between phases without requiring temperature equilibrium. The whole system is held together not by being in thermal equilibrium, but by being in pressure equilibrium. The product of density times temperature being roughly the same in all phases, even though temperature and density separately differ by enormous factors. The result is this extraordinary patchwork. The interstellar medium is more like a complex foam than a gas. Bubbles of million-degree plasma surround islands of cold, dense cloud. Cold filaments thread through warm, diffuse material. Hot gas tunnels connect separate cavities like a bizarre three-dimensional plumbing system. The boundaries between phases are turbulent, constantly being stirred by magnetohydrodynamic instabilities, by the passage of shockwaves, by the streaming of cosmic rays. It is one of the most complex fluid systems in the known universe, and it is what lies between the stars. Now, I want to come back to the disturbing implications one more time, because there's an aspect of this we haven't fully explored yet. What it means for the future. The interstellar medium is not static, it is evolving. The galaxy is not a perpetual motion machine that will run forever unchanged. It is aging. The pattern of star formation, stellar death, supernova explosions, and gas recycling that has been ongoing for the past 13 billion years will continue, but not indefinitely. The galaxy's reservoir of cold gas, the raw material for star formation, is gradually being depleted. Stars lock up gas in their remnants, white dwarfs, neutron stars, black holes. The gas that was once available to form new stars shrinks over cosmological timescales. Eventually, in hundreds of billions of years, the supply of cold gas will run out. The last stars will form. The galaxy will stop making new suns. The interstellar medium will thin out and fade. Eventually, even the long-lived red dwarfs that are forming today will exhaust their fuel and cool. The galaxy will go dark. But on the timescales relevant to us, the timescales of geological history and biological evolution, the interstellar medium will continue to evolve in ways that directly affect our solar system. The Sun is continuing its orbit around the galactic center and will pass through different environments over the next hundreds of millions of years. The local bubble will continue to expand. Eventually, perhaps 10 to 20 million years from now, the solar system will exit the local bubble and enter the denser surrounding medium. What that transition will mean for the heliosphere, for the cosmic ray flux at Earth, for the conditions of interstellar material in the solar system, is actively studied and still not fully understood. Other nearby star-forming regions, like those at the walls of the local bubble, will continue producing massive stars that will eventually explode, potentially creating new superbubbles adjacent to ours. The complicated geography of supernova remnants, hot bubbles, cold clouds, and stellar nurseries that characterizes our part of the galaxy today will continue to evolve, with the solar system moving through it like a ship, navigating ever-changing waters. And throughout all of this, the fundamental, irreducible truth remains. The space between the stars is not a background, it is a participant. It is an active, violent, complex medium through which the solar system moves, and from which it was assembled, and to which it will eventually return. Most people, when they look up at the night sky and see those points of light scattered across the darkness, experience a sense of beauty and distance and perhaps loneliness. The universe seems big, empty, and peaceful. The stars seem isolated, each burning alone in its own darkness. But what we know now is that this picture is an illusion. not a harmless one. An illusion that obscures something fundamentally important about the nature of our existence. The darkness between those stars is not empty. It is filled with the remains of stellar catastrophes. It is threaded with magnetic fields that channel the motion of charged particles across light years. It is saturated with cosmic rays, particles from supernova explosions that have been traveling for millions of years and are passing through you right now. It is a complex, turbulent, multi-phase fluid that has been shaping the conditions in our solar system throughout Earth's history, driving comet showers, increasing mutation rates, contributing to mass extinctions and evolutionary pressures. It delivered the first life-relevant organic chemistry to the young Earth, carried in the organic molecules on interstellar dust grains that fell into the solar nebula before Earth existed. We live inside a bubble carved by supernova explosions. The plasma filling our immediate cosmic neighborhood is 1,000,000 degrees hot. The solar system is being pressed against by a gentle wind of interstellar material from a local cloud. Interstellar comets from other star systems are passing through our solar neighborhood right now. Ancient radioactive iron from a stellar explosion is sitting in the sediments of Earth's oceans. The space between the stars is not a void. It is the medium in which all stellar life takes place. It is the ocean in which all the stars swim, and we swim in it too. Whether we acknowledge it or not, whether we look up at the night sky and see it or not, this is the most disturbing thing about the space between the stars. Not that it is violent, though it is. Not that it is hot, though it is. Not that it is filled with radiation, though it is. The most disturbing thing is that we have spent most of human history looking at the darkness between the stars and seeing nothing, imagining emptiness, feeling the comfortable illusion of isolation and separation, and it has never been empty. Not for a single moment in the 4.5 billion years this planet has existed. The galaxy has always been reaching into our solar system, touching our planet, leaving its fingerprints in our geology, in our biology, in the very atoms that make up our bodies. We are not separate from the cosmos. We are the cosmos, looking at itself. Let me take you on one more journey before we close tonight. Let me ask you to look at the night sky one more time, but with everything we've discussed in mind. The darkness you see is not silence. Right now, as you look at that darkness, you are being passed through by cosmic ray particles that were born in stellar explosions hundreds or thousands of light years away. Some of those explosions happened before the pyramids were built. Some happened before our species evolved. The energy in those particles was created in the death of a star, accelerated to near light speed, and delivered here, to this moment, to this planet, to pass through you. And they have been doing this every second of your life. The faint glow of the Milky Way that you can sometimes see on a clear dark night, that band of countless stars stretching across the sky, is not just stars. Between those stars, invisible but real, is a vast complex medium of gas and dust and plasma and magnetic fields and radiation and cosmic rays, all in constant motion, constantly being stirred and shocked and heated and cooled by the violence of stellar death and the gentleness of cold molecular clouds slowly collapsing under gravity. Right now, your solar system is embedded in a cloud of 1,000,000-degree plasma. You are not aware of it. The plasma is too thin to affect you in any direct way. But it is there, a vast invisible hot fog surrounding everything you have ever known, a remnant of the catastrophes that shaped the local galaxy millions of years before your species existed. Somewhere out in that darkness, right now, interstellar objects are passing through our solar system, small icy bodies from other stellar systems, wandering through the interstellar medium for millions or billions of years, drawn briefly into the sun's gravity, and then flung back out into the galaxy. Every few years, we get lucky enough to discover one of the larger ones. Most pass through undetected, carrying their alien chemistry through our neighborhood and away forever. Every atom in your body has been through all of this. Every carbon atom in your cells, every hydrogen atom in the water in your blood, every oxygen atom you inhale. They have been part of stellar cores, part of supernova ejecta, part of the interstellar medium in all its phases, part of molecular clouds, part of the solar nebula, part of rocks and ice, and eventually part of you. And after you, they will move on. They will return to the interstellar medium eventually, when the sun dies and Earth is dispersed. They will drift through the galaxy for billions of years. They may be incorporated into new stars, new planets. They may become part of new forms of chemistry, new living things, in the distant future. You are not a fixed object in a fixed place. You are a temporary organization of atoms that have been on an extraordinary cosmic journey lasting billions of years, and will continue that journey long after you are gone. The space between the stars is not empty. It never was. An understanding that changes everything about how we should see ourselves in the universe. We thought the night sky was a peaceful backdrop. We thought the darkness between the stars was absence, was nothing, was silence. It is not silence. It is the sound of a universe that has never stopped moving, never stopped creating, never stopped destroying. A universe in which every stellar death sends ripples across light years of space, touching every planet and every moon and every comet in its neighborhood. A universe in which the atoms we are made of have already traveled far beyond anything our civilization has ever attempted, and will travel further still. The disturbing thing about the space between stars is not any one fact. Not the cosmic rays, not the supernova, not the million-degree plasma, not the magnetic fields, not the constant stream of interstellar visitors passing through our neighborhood. The disturbing thing is the realization that comes when you put it all together. We are not safe observers of a distant universe. We are embedded in it. We are expressions of it. It reaches through us with cosmic rays, and through our history with supernova remnants, and through our future with the slow drift of stars past our neighborhood over the next millions of years. There is no outside from which to safely observe the galaxy. There is only this, inside the medium, inside the process, inside the cycle of creation and destruction that has been running since the first massive stars exploded in the young universe and seeded everything that came after. Look up at the stars, see the darkness between them, and know that it is not empty, it is not nothing. It is the substance from which you were made, and to which you will return, and it has never, for a single moment in the history of this planet, left you alone. Thank you for exploring this with me tonight. If this changed how you see the night sky, even a little, then the time was well spent. The universe